So let's have a look at center of gravity, center of mass. Okay, let's have a look at that. So I've got I think a little bit of a problem to work through on this, and we'll have a look at that. So we're on page 610 to start. So center of gravity, this is also center of mass, might be a better way to describe it. All right, so this is a centroid. It's it comes from the word center, obviously, and we'll use mass to get this figured out. So what we're going to do here is to break an object up into pieces, and we might do that with calculus, or we might do it with algebra. And then once we do that, we're going to find the x-bar distance to the center of mass for each piece. We'll multiply those together and then divide by the total mass. And that will tell us where what we call the center of mass is. So if this plate is 2 centimeters thick, let's see where the center of mass is. Okay. And I give you the density of the rod and the density of the plate. Now what density is the mass per unit volume. So it tells you what you have there is how much a cubic meter of this material that we're making the rod and the plate out of, how much what their mass would be per cubic meter. So if we want to find the center of mass, I'm noticing the symmetry here in the y direction. So the center of mass is going to be right in the middle there as far as y goes, but I do need to figure out the x distance. So what I'm going to do is break this thing up into pieces. Okay, the plate's 2 centimeters thick, so I'm going to find some basic information about this. So what I'm going to do for each one is find the volume based on that 2 centimeter thickness. For that first one, it'd be 0.8 by 0.03 by 0.02, 0.00048 cubic meters. And then I'm going to multiply that by the density of 8,333 kilograms per cubic meter, and that gets me the mass of the rod, 4 kilograms. Now the plate I'm going to do in 2 steps. I'm going to find the volume of the entire plate, which would be 20 centimeters by 30 centimeters by 2 centimeters thick. So I'm keeping there in cubic meters. So I got 0.2 times 0.3 times 0.02. So that's 0.0012 cubic meters. And then I'll multiply that by the density and get 1.478 kilograms for a full plate. But then I've got a circle cut out of the plate. So that'll be a negative pi times the radius of the circle squared times the thickness. And then I'll multiply that by the density of the plate and get a negative density for the circular cutout. Okay. So I'm just going through and getting kind of this information set up for this. Because once I have that stuff set up, I can just fill in that table and then get this stuff figured out. Okay. Now, to find these center of mass and centroid, I like to use a table because it just organizes my work and helps me cut down on errors and things like that. So I'll go ahead and do that. Yeah, question there?
For the circle cutout, why negative pi?
The negative refers to the whole expression for the circular cutout. And the reason it's negative is it's a cutout. It's being taken away. Oh, so I don't think of it so much negative pi. The negative affects the whole thing. Yeah. Okay. All right. And it is important when you're doing these, make the cutouts negative. Okay. All right. All right, and then it's just a matter of filling in the tables. So I've got the volume and the mass for the rod, and then I want to figure out the x-bar distance. And what I'm doing for the x-bar distance is I'm taking half of the length. So the length is 80 centimeters, which would be 0.8 meters, but I'm going to the middle of that. Now I'm measuring from point A to the centroid of the rod. Okay. And so then what I do, I take the mass times that x-bar distance, and I get 1.6. I've got my units up on the top there. So I got meters cubed, kilograms, meters, and kilogram meters on the top. And I'll just run through and do that for each of the shapes. So the table just allows me to organize everything. And, that's, I think I mentioned this before, that's, it's a good thing to be able to do, in school, but when you work too. I mean, just line this stuff out. Don't have it all over the place. Nice and tight and organized and less errors. And everyone's happy then, okay? All right. And so then we go through and we just do the deal on this. So we're going to do the solid plate as though it had no cutout. So the volume of that is 0.0012. The mass is 1.478. The x-bar distance is from A to the center of the plate, which is 0.90 meters. Okay, so I'll take the 1.478 times 0.9 and I'll get 1.33. And then I'll do the same thing for the cutout. So I just run through this process repetitively. I really don't need the volume in this table because really all I use is the mass, and I already calculated the mass. But if I were using this to calculate, I might have that volume in there. When I look back on this, I really didn't need a column for volume because I already used it to get the mass. The mass is what matters. So the volume there on the circular cutout we got the mass at negative 0.278. The x-bar distance is 0.9. So when I multiply those together, I get the total mass times x-bar. Okay. And then once I've got that stuff, what I'm going to do, I'm going to total up the mass, and I'm going to total up the mass times x-bar for each shape, and then I'm going to divide the mass into the mass times x-bar. And what I'm getting out of this is a weighted average is what I'm going to get, which is where the centroid's at. Okay, so the total of mx bar is 2.68, and the total mass is 5.2. So I'll just divide those out and get 0.515 meters. Okay, so that's where the centroid is. That's the balance point of the object. It's right about there. I always like to plot these up and have a look. That looks about right to me. That's 0.515 meters over. That, if I tried to balance that object, that's about where it would balance. That looks about right. Okay. So there you go. All right. So that tells me where the center of mass is for that thing. All right, and then just kind of incidentally here, if you took that object and threw it, the center of mass is the point about which it would rotate. Okay. And, I'm not sure if they still have you do projects in physics or not. They used to quite a bit. And there's a project there. They put LED lights on an axe, I think. The bright one's on the center of mass, and then the lighter one is on the end of the handle. And they just threw it, and waited at night, of course, when it was dark, and you could see the lights through the axe, and you see the center of mass there has a nice clean parabolic trajectory, and they put a time-lapse photo together there. Yet the point of the handle is kind of that odd motion as it's going. So that center of mass is the point that has the nice clean trajectory, and then the object itself rotates about the center of mass. Okay, all right. So that's kind of one reason why we might want to know where the center of mass is at. Okay. All right. So that's a property of an object, the center of mass. So are we good with that? Any questions? All right, now another property that's quite a bit more abstract actually, is a mass moment of inertia. And that follows, it's on page 620. Okay. So I contrast this with an area moment of inertia. They're related things, but they're different. If you're taking strengths right now, and also in statics, you probably figured out how to calculate an area moment of inertia. That's for a cross-sectional area. It kind of relates to how an object flexes and bends when you load it up. This is a mass moment of inertia, and this is going to relate more to angular acceleration. Okay, so let's say we've got this cylinder here, and we want to make it rotate. So let's say that line there comes out of a motor that we've got down here, and we're going to take that motor and apply a torque to that shaft there that connects it through the cylinder. The mass moment of inertia gets us an idea of how hard it is to get that thing to start to rotate. So it relates directly to the angular acceleration. Okay? So the mass moment of inertia fits into an equation that looks like this that we use a lot in dynamics. Its sum of moments is equal to I, which is the mass moment of inertia, sub g, about the center of gravity, times alpha. Okay? So what that mass moment of inertia tells you is if you exert a certain moment or a certain torque, and in the mechanical world you commonly do that out of a motor and turn a shaft and exert a torque on something, it tells you how hard it's going to be to make something accelerate and have an angular acceleration. So it depends on three things: the mass of the object, the shape of the object, and the location of the axis about which the object rotates. So those are the three things you look at when you're finding moment of inertia. The core definition of it is the integral, meaning to add up a distance, r, which you square, and then you break the object up into a bunch of little submasses, dm's, and then you look at how far you are from an axis, you square the r and multiply it by dm, okay, and then add all those up. All right, so we okay with that? That's the fundamental definition of moment of inertia. Okay, now you can look at that definition and get some idea, how you might want to configure things. A flywheel often has a lot of the mass out a long way from the axis about which the thing's going to rotate. So your R is out there, and then we've got a dm. So here's your dm, and there's your R. Okay? So your r squared dm then, what we're doing there when we find this moment of inertia, if with a flywheel and with a lot of objects in engineering, we want a high moment of inertia. So what you do is you take your mass and you set it out a long way away from the axis. Okay. Y'all with me there? Okay. And that's how that's done. Okay. And I've got a little video in Moodle that relates to this, that has a flywheel, and you might want to have a look at that if you're online. Okay, and just to get an idea. All right, and so as we were talking about in class, the purpose of that very large flywheel there was to smooth the motion out. You don't want intermittent kind of jerky motion on something that's rotating in a machine. It causes vibrations. It can cause a lot of stresses and things in the machine. So the purpose of a flywheel with a high moment of inertia is to get a nice smooth motion. Okay. All right, now let's look at how to calculate one of these. And let's do this a couple of different ways. And this is first let's start on page 630. We just have a disc, basically a hockey puck here. All right, and let's go to the fundamental definition of this, and let's find that, that moment of inertia for that thing. So what we're going to do is use what in calculus they call the shell method. We're going to cut a bunch of thin rings through the disk. The reason we're going to do that is that'll work well with our definition, because a circular ring has one radius on it. So that'll be the r, that'll be the distance from the center, the z-axis that we're using to calculate this moment of inertia. We're going to measure out from that, and then we're going to go on a little ring there, which we call a shell. Now the area of the shell will be the circumference 2 pi r times the thickness, which is dr. Okay, so what I'm doing, I'm taking this shell, I'm cutting it, and I'm laying it out flat. So to get the area of that, it's the circumference of the shell, the length times the thickness, the dr, so 2 pi r dr. Now to get the volume, I'm going to multiply it by the thickness. I want to be in meters here, so I got 0.07 meters. And then to get the mass of a shell, I take all that and multiply it by the density. When I put all that stuff together, I get the mass of one shell. It's 792 times RDR. Okay, so that's what I'm putting together. And then I add them up, which is what an integral does. So I'm going to start at the middle, which is R0, and go to the outside, which is R equals 0.12 meters. So that's the formation that I'll use, or the formulation, whatever the heck you want to call it, to find that moment of inertia. Okay. So I'm going from 0 to 0.12 r squared, because that's part of the formula. The dm is 792 rdr. And I pulled the 792 out because it's a constant, and I integrate the r squared. That's r cubed. No, I didn't. I've got r squared and I got an r in there. So r squared times r is r cubed. Then I integrate that and get r to the 4 over 4. There we go. And then I plug in 0.12 into that and 0 and take the difference. Multiply that. I pulled the 4 out is what I did. And then I took 0.12 to the 4 minus 0 to the 4 and multiplied 792 over 4 times that formulation there and got 0.04106 kilogram meters squared. That's what I got. Are we all right with that? The integral there? Okay. Now that's the fundamental. That's applying that fundamental definition and knocking through that. Okay. Okay. Now let's use the tables on the formula sheet to do this. See, this is using calculus, but if you go on tables, you've got one person who's done the calculus and then he wrote the answer down on a table and everyone else can go get it. Okay, so that's all right. Okay, so that's on the back of the formula sheet. I've got a bunch of moments of inertia. All right, and so what I see there, here's the formula sheet, the back of it. I'm going to go to a disk, which is what I'm dealing with right there. And you just got to pay some attention to the axis you're talking about. This one's pretty obvious. I mean, we've got an axis that's perpendicular to the flat face. All right, so we want to use the formula here that has an axis that's perpendicular to the flat face. We called this one Z, this one's called Z. It's all good, okay? So the formula there for IGZ is 1/2 mr squared. Okay, I got the mass calculated there. The density times pi r squared times the thickness, it's 5.7 kilograms. Okay, and then I just plug in everything and out comes the same answer as I got using calculus. Okay, so these tables, you'll have them, you know, obviously you got them. Anybody need a formula sheet? I got a few up here if anybody wants one. They're the blue formula sheets. You know, you have those, you know, and you get them on a test and all that. So, you know, if you've got a regular shape and I've got a sphere, a cylinder, a disc, a hollow ring, a plate, and a thin rod on there, you can just use the tables, see? Okay. All right, now, when you start putting composite mechanisms together, it's quite common that you don't have a rotation about the center of mass, or the centroid, you might say, because this sheet here is built for centroidal axes. That's what it's made up for. So you might get into a situation where you need to find the moment of inertia of a shape about an axis other than a centroidal axis. So you might have some sort of offset axis here. If that's the case, you use the transfer axis theorem. You take the moment of inertia of axis through the centroid, then you add a term to account for this offset. So you take the distance, you square it, and multiply it by the mass, and that's called the transfer axis theorem. So I about that axis there would be the sum of IG plus MD squared. Okay. And you can see the effects of this. I've got two identical objects there, and you can see I got one on the left and one on the right, and I've got a real simple axis put through there with a pencil just taped onto it. And you can imagine what happens if I try and spin those. You know, which one's harder to rotate, the one on your left or your right, do you think? Yeah, the left there. No, I don't know about that. I think left, right. I think right's going to be the hard one there. It's a little out of balance, right? A little bit harder to start that to spin. See, and here's that transfer axis thing. See, this goes right through the center of gravity here. This doesn't. So you get a higher moment of inertia there on account of this offset distance. A little harder to get that spinning, okay? Okay, and there's a formula that you can derive for that. You know, if you use this formula I've got here was actually developed for the area moment of inertia, but it's the same thing. I don't think I put that derivation in there in your dynamics packet there because we already did it in statics. But basically what you would do here to find, to derive this thing is you've got I bar sub x is y squared dm. If you set up a new axis here, okay, so here I have the axis that goes through the centroid, and that's just y squared dm. If I set an offset axis a distance of d away, each one of those y's there is going to become a y plus d. So instead of y squared dm, I'm going to get y plus d squared dm. So I'm going to have to expand that. That's a quadratic. So I'm going to get y squared plus 2 times d times y. That's not a calculus dy. That's a d times a y plus d squared dm. All right, and then I'll just factor that dm through. So I'll get y squared dm, 2d y dm, and d squared times the integral of dm. So I've got integral signs in there. So the integral of y squared dm, 2d times the integral of y dm, and d squared times the integral of dm. Okay, y squared dm is just the centroidal moment of inertia. Okay, that's all that is. So that will become I bar x. Okay. D squared times the integral of dm will just be md squared. The term in the middle will actually zero out because for every positive y times dm, I'm going to have an equal and opposite negative y dm because I'm measuring for those y distances from the centroid there. So that middle term zeroes out. So that's where this formula comes from. Okay. So why don't we look at this situation with that disk. Let's put a pin joint through A. And let's get an indication of how hard it would be to make this disk rotate about that pin joint. So let's find the moment of inertia of that disk about a point on its edge there. Okay. So we've already gone through what the moment of inertia is for this shape. Okay. Now what I'm doing, I've kind of flipped it a little bit, but I still have a z-axis that does that. Like that. Okay. So when I find the moment of inertia of that disk about that z-axis, that's the 1/2 mr squared. That's the 0.04106. Okay. Now if I want to find I sub a, what I'm going to do is I'm going to take that number and I'm going to add the mass of the disk plus the offset distance squared. Okay. That's what I would do. So I'll take the 0.04106 plus the mass, which I've calculated up here, times the radius, the 0.12 squared. Okay. And I'm just going to add those together and get 0.123 kilogram meters squared for that. So there's the moment of inertia, which is, quite a bit larger, 3 times larger than the moment of inertia of the centroid here. The centroidal moment of inertia is 0.04, whereas the moment of inertia through this point A is about 3 times as large. So when you start using these offset axes, it can really affect the moment of inertia of the shape. We got any questions on that? Okay. Yeah, it's similar to statics. Remember, statics is area moment of inertia. This is mass moment of inertia. They're different things, but they're related things, and certainly in how they're calculated, but they are different in their function. Okay. All right, and then we can do a more complicated run through a more complicated problem, but we're out of time, I think, so we'll call it good on that. I don't know if you want to. Why don't I assign what all I'm going to assign? This will be due Friday, so it's a ways out. But I'm just thinking about it, so why don't I assign it? So I'll get you 321, 322, and 324. So 321, 322, 324, and those will be due Friday. Okay, remember we have our test coming up. So Friday will be the 24th. We got our test coming up on Wednesday. So we all right with that? Okay.
If you say no, does it matter?